theory-led models really start to lose their shine. And I think that machine learning is at this forefront of a revolution of what I guess could be called data-led models, or the data revolution, so to speak. As opposed to theory-led models, actually, sorry. The thing is not working. Okay, the video is not running. Anyways, as opposed to theory-led models, data-led models try not to impose too many assumptions on the processes that we want to model, and are rather super flexible, non-parametric models that can capture the complexities, but that require large amounts of data to operate. Of course, there's not really a dichotomy between theory and data. We always need both. I really enjoyed Ali Rahimi's talk 2 days ago. But I think that there's a difference between trying to squeeze the data through very simple models versus letting the data speak for itself. I guess because our detailed understanding of these complex processes is really lacking in many respects, while at the same time we now have access to large amounts of data on the same processes. I guess this is just paraphrasing what Brendan Fry was talking about in terms of biology, where it's such a complex process that we as humans, we can't really understand all the intricate details, and we really need machine learning and artificial intelligence to help us process these things. And I think that machine learning is crucial here as it opens up the possibility for us to work with such processes. Okay. So anyway, personally, I find this view helpful in understanding some aspects of the history of machine learning over the last few decades, as a history of growth, both in model complexity and in model flexibility, and to accommodate this ever more complex processes that we want to work with. So on the model flexibility side, we have various non-parametric approaches that has been explored over the years. We have kernel methods, Gaussian processes, Bayesian non-parametrics, and now deep learning as well. The community has also developed ever more complex frameworks, both graphical and programmatic, to compose large complex models from simpler building blocks. So back in the 90s, we have things like graphical models, and then we have things like probabilistic programming systems like Church and Anglican and Stan and Venture, to deep learning systems like TensorFlow and Theano and Torch. And most recently with things like Edward and Pyro and probabilistic Torch, systems that are starting to bring together ideas from both the probabilistic Bayesian learning side of things and the deep learning side of things. Which kind of brings me to the topic of my talk, really, which is at this interface between these two very important ideas that's been quite dominant in machine learning. On the one hand, we have this Bayesian learning, which views learning as inference in some probabilistic model. And we have deep learning on the other side, which views learning as optimization of flexible functions parameterized by neural networks. So I think these are quite complementary ideas. And in recent years, there has been an explosion of exciting research at this interface with increasingly complex and flexible models that bring the best of both worlds together. I have to say that I've been actually really amazed by the awesome progress that's been made over the last few years. And it's only actually quite recently that I've kind of joined the fray in terms of exploring ideas around this interface. So in the rest of the talk, I'll talk about a few projects that I've been involved in. But before that, I'd like to give a bit of an introduction to Bayesian learning, as I think that not everybody here is necessarily familiar with it. Okay, so talk about this. So the Bayesian theory of learning basically describes an ideal learner that is interacting with the world. It wants to learn something about the world, but it doesn't know the state of the world. Right, so, and here the state of the world is given by theta, but it does make some observations with which it can learn about theta. And the way that it goes about doing this learning is to first start with, to posit a model, which is, in the Bayesian context, is a joint distribution over the unknown theta and the observed x. And this model consists of two parts. We have the prior here, right, which is the marginal distribution over theta, and what it does is it captures the prior knowledge that the agent brings to the problem, and the assumptions that the agent makes about the world, before it sees any data. And then we have the conditional distribution of x given theta, called the likelihood, which describes the process by which observed data is generated assuming that the state of the world is given by theta. We can now combine the prior and the likelihood using the calculus of probability. We basically just turn the crank, and that gives us the reverse conditional distribution here. This is by Bayes' theorem. And this reverse conditional distribution is now going to be of the state of the world theta given observation x. And this is called the posterior, and it captures, in a sense, the totality of the agent's knowledge about the world after it sees x. And one way you could think about this posterior as is describing all the states of the world that are consistent with both the prior and the data. Okay. And this is a set of states. It's not a single state. And this is kind of the key difference between Bayesian learning and kind of something like maximum likelihood, which just optimizes and figures out one of the states of the world which explains the data. So it captures more of the uncertainty that the agent doesn't know about the world. And once the posterior is computed, the learner can use it to predict on future observations, and it can act by choosing actions that maximize expected utility, for example. So I've been at NIPS for many years, and for those of you who've joined recently, so for those of you who have been around for a long time like myself, you remember back like 10 or 15 years ago that Bayesian learning was very popular. I can't resist actually showing this plot here actually, even though it doesn't really relate necessarily to the topic of my talk. And what this plot shows is kind of demonstrates that actually what it does is, what this is about is following. So we kind of applied a Bayesian non-parametric dynamic topic model to NIPS papers in the years 1987 to 2015, and we estimated the probabilities of the topics appearing in papers across the years. And what it shows is that in the early years of NIPS, we have the dominance of connectionist models, connectionist ideas, and that decayed over time. And it also showed the gradual rise of Bayesian and probabilistic models. And now, after about 2012, the explosion of deep learning. I didn't show other topics here, but there was also one topic on kernel methods which peaked around year 2000. Anyways, so Bayesian learning was popular, and part of the reason for their popularity is, I think there's a few good things about it. Firstly, the framework tells us something about what a perfect learner would do if it has access to unlimited computational resources, if it makes the assumptions that we make, and given the observations that it sees. This is useful because it tells us something about which direction we should be heading, even though we can't compute this perfect learner exactly. It makes explicit all the assumptions which goes into the learning process, and it gives a unified treatment of uncertainties, both in terms of partial knowledge about the world and also observation noise as well. And this can be important in applied settings where risks due to errors need to be well controlled, or at least well calibrated and well understood. Finally, it gives a common language in which we can actually talk to other statisticians and applied scientists. However, I think that the Bayesian approach to machine learning is, there's some problems with it. The first problem is a problem of rigidity. I think it's basically an axiomatic approach. We start off with basically axioms or assumptions that we make when we set out the model. And unfortunately, if those assumptions are wrong, then the learning that we make may be completely wrong as well. And it's kind of difficult to test for this in the Bayesian context. You kind of have to step out of it. Further, not all prior knowledge about a domain can be easily encoded as joint distributions. My favorite example here is ConvNet's InVision, right? So because that says something about the structure of the computations that we have to do to label an image and how it generalizes to changes in that image, rather than how an image is actually generated. Finally, in order that computations are tractable, traditionally the conditional distributions that make up the building blocks of Bayesian models have taken very simple analytic forms, and I think these forms are very limiting in terms of what we can model. There are also scalability issues in Bayesian learning. Often it's intractable to compute this posterior exactly, and approximations have to be made, which then introduces trade-offs between efficiency and accuracy. As a result, it's often assumed that Bayesian techniques are not scalable. So in the rest of my talk, I'd like to highlight a few recent projects that I've been involved in, which addresses some of these issues. In the scenario where we apply Bayesian ideas to neural networks, i.e. Bayesian deep learning, or in the reverse, where we apply deep learning ideas to Bayesian modeling, i.e. deep Bayesian learning. Okay. So the first project is going to be called Posterior Server, and it's about a distributed system for doing deep learning for neural networks. And what I like about this project is that by taking this Bayesian approach, we can get perhaps counterintuitive and surprising ways to make deep learning scalable. Okay, so just to set the stage here, what we're interested in is learning about the parameters of a neural network, which in this case we can just think of as simply parameterizing a flexible function that maps from inputs to outputs. We assume that we have a prior over parameters, which is typically just a Gaussian, while the probabilities of outputs given inputs in a data set gives us the likelihood function, and the object of Bayesian inference, the target, is to compute this posterior distribution over the parameters given the data. As an aside, if instead of computing this full posterior, we simply find a mode of it, then that gives us the usual regularized maximum likelihood. Many people have worked on this Bayesian neural networks for a long time, and I guess that most of the algorithms can be gathered into two large classes. Markov chain Monte Carlo sampling algorithms, which construct a sequence of random samples of the parameters, which converges to the posterior, and variational inference, which posits a parametric form for the posterior and optimizes the parameters of this form to minimize some divergence, like KL divergence, to the true posterior. So in this project, we focus our attention on distributed learning, where both the data and the computations are going to be spread across a network. So we have a bunch of workers, and they're going to each talk about, they're going to each communicate with a server. And typically when people think about distributed learning, they think about optimization-based methods, things like stochastic gradient descent, done in some asynchronous way across this network of workers. And it's managed by this server, which is called the parameter server. It's called a parameter server because it effectively maintains the authoritative copy of the parameters of the network. At each iteration, each worker obtains the latest copy of the parameter from the server, computes a gradient update based on its data, and sends this back to the server, which then applies this update to the authoritative copy. So communication over the network tends to be slower than computations that can be done on the worker. So one might consider actually multiple gradient steps on each iteration before it sends the accumulated update back to the parameter server. The problem is that the parameter on the worker quickly gets out of sync with the authoritative copy on the parameter server. And as a result, this leads to stale updates, which adds a lot of noise into the system. And as a result, we often need very frequent synchronizations across the network for the algorithm to learn in a stable fashion. Our main idea here is that in a Bayesian context, we don't just want a single parameter, we actually want a whole distribution over them. And if we have a distribution over them, it's actually okay if every worker has its own copy of the parameters, so long as every worker is sampling from the same posterior distribution. This will then relax the need for very frequent synchronizations across the network, and hopefully lead to algorithms that's robust to less frequent communication. So now the role of the server becomes not to maintain this authoritative copy of the parameter, but rather the posterior distribution. That's why we call it a posterior server. The question then is, how does the posterior server construct this posterior? Because that has to be dependent on the data across all the workers. So at the high level, what we do is the following. So each worker is simply going to construct its own tractable approximation to its own likelihood function. And it's going to send this approximation to the posterior server, which can then combine all of these approximations together to form the full posterior, or an approximation of this full posterior. Further, the approximations that are constructed on each of the workers are going to be based on the statistics of actually a local MCMC sampling algorithm that happens locally on that worker. Okay. So the actual algorithm is a little bit complicated. It involves a combination of a variational algorithm called stochastic natural gradient expectation propagation and Markov chain Monte Carlo sampling on the workers themselves. So the variational part of the algorithm basically handles the communication across the network, while the MCMC part handles sampling from the posterior that's local to each worker to construct the statistics that the variational part needs. And for scalability, we use the stochastic gradient Langevin algorithm, which is a simple generalization of SGD, which includes additional injected noise here, which forces basically the samples not to converge to a single point, but rather to jump around and sample from the posterior distribution instead. Okay, so we demonstrated our distributed Bayesian learning algorithm via a number of students and graduate students at the time. Don't have a lot of resources. Anyways, so in the first experiment, we trained densely connected neural networks with 2 hidden layers, 500 and 300 ReLU units on MNIST. And in this figure, we show that the algorithm is robust against infrequent communications with the server. What we did was we basically varied the number of learning iterations in between communications with the server all the way from 1. So basically every learning update, we communicate with the server to 100. So we only communicate with the server every 100 iterations. And we see that this actually barely affects the algorithm at all. So it slows it down a tiny bit, but not by that much. We also varied the number of workers from 1 to 8 in this case, and find that our method scales pretty well as the number of workers is increased. We didn't find in this case that it helped once we go beyond 8, I guess because it's a very small data set. We also compared against a number of state-of-the-art baselines. So our method, SNAP and Power Snap, works significantly better than asynchronous SGD. One version actually works much better than Adam, but elastic averaging SGD works even better in this case. On a different architecture where we have 20 fully connected layers with 50 units each, Adam completely fails in this case, while our method actually works significantly better than asynchronous and elastic averaging SGD. Finally, on a convolutional network applied to CIFAR 10, again, it beats state-of-the-art in terms of speed and achieves comparable final accuracy to the best baseline, which is Adam in this case. So before I move on to other projects, I'd like to kind of give a shout out to some nice work that were done by others at DeepMind, but relates in an interesting way to this posterior server work which I just described. So at DeepMind, what we're interested in is progress towards AGI. And one of the things that we'd like to do is to be able to train agents in which the single agent can behave intelligently across different domains and different contexts and different tasks. We're also interested in an even harder situation where the agent may interact with and train on each task for a period of time before moving on to the next one. One of the problems one encounters when training agents in such a continual learning setting, particularly when using standard learning algorithms like SGD, is that of catastrophic forgetting. And what it is basically that it's a phenomenon in which as we learn on subsequent tasks, the agent actually forgets how to act in previous tasks. So it just kind of forgets about it. So at a high level, the method that Kirkpatrick et al. Came up with which is called elastic weight consolidation. It works exactly like a sequential version of this expectation propagation algorithm, which is the variational method that our posterior server work is based on. And the reason why this works for continual learning is actually because in the ideal Bayesian learning case, actually it trivially solves this continual learning problem. So basically the posterior given data from both tasks in this case is the same whether the data is shown one at a time or all at once. It doesn't actually matter to this ideal learner. Of course, this ideal learner is intractable, and the idea in EWC is to approximate the posterior with an tractable approximation called Laplace approximation, which uses an estimate of the Fisher information matrix. Of course, this works well. You can look at the paper for more details. Before I move on to the other projects, I'd like to say a few words about Bayesian neural networks. So in our work and in most other applications of Bayesian ideas to deep learning, the aim is to compute the posterior over the parameters of the neural network, given prior and data. However, there's, I think, a problem here, and the problem is that actually the parameters in neural networks often don't actually have any real meaning, right? Because you can permute the units, it doesn't change the function at all. And it's not really clear how one can specify sensible priors for them that is not just sort of like a weight decay sort of prior, but further, and also further, basically the posterior becomes highly multimodal and complex because of these symmetries. Right? So as a result, I think it might be better, just a question for everybody to think about, might be better to think about priors and posteriors not in the space of parameters, but rather in the space of functions, okay, that the network parameterizes. So in the first project, I've described how Bayesian ideas can help produce interesting learning algorithms for neural networks. In the next two projects, I would like to describe the converse, which is how can deep learning ideas improve Bayesian learning. Okay. And there are two ways to do this. One is we can improve the modeling flexibility by using neural networks in the construction of Bayesian models. So this relates to the question of rigidity in traditional Bayesian models. And another is to improve the inference and scalability of these methods by parameterizing the posterior using neural networks and by amortizing inference over multiple runs. So both of these are actually clearly seen in a class of deep generative models called variational autoencoders. So these were proposed by two very nice papers by Kingma and Welling and Resende et al. Over in DeepMind. The generative model is that we have latent variables Z, which describe the contents of a scene, and we have some observed image of the scene, say. And of course, the relationship between these latent variables, which might describe things like objects and their pose and so forth, the relationship between those latent variables and the pixels in the image has to be highly complex and nonlinear. And they basically use a neural network to parameterize this relationship. And we are going to learn that as well. Now, to learn this generative model, we use variational inference. And what this does is, what we like to do is to maximize the log likelihood of our observed data, integrating over the latent variables. We can't do that because that integration is intractable. So we construct a tractable lower bound on this log likelihood called the evidence lower bound, or ELBO for short. And this lower bound is described by a variational posterior Q, which is also parameterized by a neural network. And I think that using deep networks to parameterize both this generative and the variational posterior distributions allows for great scope for flexible modeling. And some of the recent models have been mind-blowing, at least to me. Just to give an example, so this is a draw model that came out of DeepMind. It's a deep generative model for images, where an RNN is used to draw an image by successfully refining it over a few iterations, with each iteration driven by a latent random variable. The variational posterior is itself an RNN, which tries to reconstruct the latent variables given the image. So this learns really well. If you show it bunch of handwritten digits, it generates handwritten digits which are pretty much indistinguishable from the real ones. If you show it straight numbers, it produces straight numbers. If you show it the CIFAR 100 data set of 100 object classes, it produces images in which, if you squint at it, it looks like CIFAR images. Perhaps this is pretty old news by now and not state of the art anymore, but I still find this amazing relative to what we can do even 5 years ago. So now, the key which makes VAE's work actually is something called the reparameterization trick. Okay. So the idea here is that it's difficult to directly optimize the parameters of the variational posterior because it appears as the distribution under which we are taking expectations in this ELBO. So what we do is we rewrite this ELBO in terms of an expectation over some standard distribution, and we basically push the parameterization of Q into the integrand itself. So that's given by this formula here. So now derivatives with respect to the parameters of both P and Q can be easily estimated in an unbiased way. And this can now be plugged into SGD, and we can now learn these variational autoencoders. So the reparameterization trick is critical to the success of VAEs. However, there are many models for which maybe the latent variables are naturally discrete. So it works originally only for continuous latent variables. So anyways, there are situations for which we do want discrete latent variables. So for example, we might want to model the presence of or absence of features or of objects. We might want to model the number of objects in the scene. We might even want to model things like, we might want to use discrete data structures like trees and graphs, or have control flow in our generative model. And all of these are discrete decisions that we have to make. The question is whether we can come up with something like the reparameterization trick, but for discrete random variables. And the answer here is, of course, yes, by relaxing this discrete random variables into something which we call concrete random variables. Okay. So the idea is as follows. Suppose we have a discrete variable z with some anomalized probabilities alpha 1, alpha 2, and alpha 3. We can construct a sample from z using this computation graph. And what this computation graph does is the following. It takes the log probabilities, it adds some noise to them, and this noise has to be Gumbel distributed. It's distribution, kind of a standard statistical distribution. And then we just take the argmax of this. Okay. And it turns out that because of the magic of Gumbels, actually that the randomness introduced in this process actually makes the sample that we construct have exactly the desired discrete distribution that we want here. The basic idea now is to replace the argmax, which has zero derivatives almost everywhere, with a softened version of the argmax, which is just a softmax at some parameter lambda. This produces a distribution which is now supported on the interior of the probability simplex, which we call the concrete distribution for continuous relaxation of discrete distributions. So in concurrent work, Eric Zhang et al. Had called this the softmax Gumbel for obvious reasons. Further, because now every step of the computation graph that I described here is differentiable with non-trivial derivatives, we can now backpropagate the gradients through to the alphas, from here all the way through to the alphas, and so this is basically a reparameterization trick. Okay, and we can now also derive a density for this distribution, which turns out to be useful in computing KL divergences needed for variational inference. So just to show some results, in experiments where the task is to predict the lower parts of MNIST digits given the upper parts, we showed that this leads to state-of-the-art results for VAEs with discrete latent variables. It's also recently been extended by work called REBAR, actually by George Tucker et al. It was just presented yesterday. It was a very nice talk in the morning. And the idea here is to combine this concrete idea with the reinforced trick. Okay? So I didn't know that there's a word for this, but basically rebar is basically these steel bars that are put into reinforced concrete. Okay? And the idea here is the following. So the reinforced trick, this is also sometimes known as the score function estimator. It gives unbiased but high variance estimators of the gradients that we need. But it has very high variance. And the key idea here is that we can use this concrete trick to actually as a control variate for reinforce, and thus we can reduce the overall variance while keeping it unbiased. So this work has itself been extended by people in Toronto, where they learned the control variate itself. It's, I think, quite amazing how quickly these things progress these days. I can't quite keep up, I think. So that's the second project. The final project is called the Filtered Variational Objectives, or FIVO in short, and it extends VAEs in a different way towards models for sequential and time series data. So it's built upon another extension of VAEs called importance-weighted autoencoders, or IWA for short. So IWA is based on rederivation of this variational lower bound using an idea from statistics called importance sampling. And the idea is very simple. We can first write our marginal probability of data given parameters as an expectation over the prior, over Z, of the probability of x given the latence z. Now we can rewrite this expectation as another expectation now over the posterior, the variational posterior, which in the important sampling case is called the proposal distribution. And of course, we've changed the distribution under which we take this expectation, and we need to correct for that. And that correction in important sampling is basically done by this ratio of P over Z, P of Z over Q of Z. Okay. So this is just equality, it's easy to show. Now if you take the logs on both sides, and you push the log into the expectation using Jensen's inequality, you get this variational lower bound given in the top equation here. So the observation in Yee Whye is that instead of using a single sample from important sampling, we use multiple samples. We're going to get a tighter lower bound, and optimizing it should lead to better learning. And the idea in 5.0 is basically now straightforward. We can use any unbiased estimator of the marginal probability to form a variational lower bound. And for sequential models, there's a large class of methods called particle filters or sequential Monte Carlo, which does produce these unbiased estimates with much lower variance than important sampling. So should produce much better variational objective. So this is concurrent work also with people in Columbia and in actually Oxford by a different department as well. I guess an idea that has, whose time is ripe, I guess. Anyways, we applied 5.0 to variational RNNs. So these are sequential models where we have a sequence of observations X that we want to model, and we model it with a sequence of IID latent variables. And these latent variables are basically passed through an LSTM. Okay. So given an observed sequence, X, we might be interested in inferring what were the likely values of the latent variables that are consistent with this observation sequence. And particle filters allow us to do this by constructing a Monte Carlo estimate of the posterior one step at a time. Okay. So at each step, we have a collection of particles. Each is a sample from the posterior given observations up until that point in time. And for the next time step, each particle proposes the next state from a proposal distribution, which we're going to learn. And then a resampling step happens. And basically what this does is that the resampling step looks at the states that were proposed, and it compares this state to the observations at that point in time. And it says, whether that state is consistent with the observation. If it is, then it's going to be duplicated. It's going to have more children. And if it's inconsistent, then it gets basically killed off. Okay, so something like this. Yes, and what this resampling step does is that it basically focuses the computation on the parts of the space where the particle filter things has high posterior probability, right? It's kind of like, it's a good management of computational resources to focus on parts of the space which are more promising. And this is repeated at each time step over the sequence. And the interesting thing with this particle filter is that at each time step, we can get an unbiased estimate of the conditional probability of each observation given past observations. And now applying Jensen's inequality as before, we can get a lower bound on the log likelihood of the observations, which we can now optimize with respect to both the proposal distributions and with respect to the parameters of the RNN. So we tested 5.0 against Yee Whye and the original elbow objectives on variational RNNs and applied this to a range of sequential data, and we found that it works much better than other baselines, either the Yee Whye baseline or the elbow baseline. So that kind of concludes my talk. I'd just like to end with a few final remarks. I think that this interface between Bayesian learning and deep learning is a very exciting frontier. There are a ton of great work being done by all sorts of people, lots of people in this audience, and really I'm kind of here mostly to cheer you guys on. Okay, it's very exciting. And for those of you who want to learn more, I hope that you've seen lots of great papers at the main conference, and there are also good workshops for you to attend as well over the next few days. So I'd like to end with maybe two questions to think about. One I've already brought up, which is that being Bayesian in this space of functions could make a lot more sense rather than being Bayesian in the space of parameters. So this relates to things like Gaussian processes and stuff. And another question which I think has been bugging lots of people here is how do we deal with uncertainties when our model is wrong? Because our model is often wrong, even if we could make it very flexible and we can learn it. And the problem with this is that once the model is wrong, it's very difficult for us to say whether our uncertainties that we get from the posterior is going to be calibrated or not, and we need to fix that, I think. So I'd like to end by thanking the NIPS organizers for a spectacular conference, funders for my research, and you for listening. Thank you.
So please come up to the microphones if you have questions for Yee Whye. We have plenty of time.
Yeah. So you talked about the symmetries in deep neural networks and how this makes the posterior very complex and multimodal. Do you have any idea if that's just due to the symmetries? So like if we could remove the symmetries or control for them somehow, would we still have a complex multimodal posterior for neural nets?
I think that would be interesting. I don't have very specific ideas. I just feel that it's a problem because of the symmetries. And if you have great ideas, I'll see the paper at the next NIPS.
Okay, I have a question. So, so in the posterior server, you around a multimodal estimate of the posterior? Because it wasn't from your diagram, you looked like you had some Gaussians that were just overlapping.
Oh, okay.
So the question was, in the posterior server, do you have a multimodal estimate of the posterior that you maintain? Or is it somehow a unimodal reconciliation of the local?
It is a unimodal reconciliation, actually. So we're making basically a Gaussian approximation for the posterior. So there's a question there?
So you mentioned theory-led models in the beginning of your talk.
Sorry?
So you mentioned theory-led models, scientific theory-led models in the beginning of your talk?
I'm not sure. I'm not sure I understood
that. So the beginning of your... So the beginning of your talk mentioned theory-led models.
Okay.
I would like to get your thoughts on using priors or using scientific knowledge to form priors over functions, where the scientific knowledge can range from closed form equations like the laws of gravity to more complex forms like dynamical systems involving partial differential equations, like used in Schrodinger's equation or Navier-Stokes equation.
Okay. Yeah, I think that's a great question. I think that it makes a lot of sense to actually use scientific theory to help us specify priors, and that relates to this question of function space view versus parameter space view, because these priors are often expressed in terms of the function that we want to compute. And it makes sense to put priors on those functions like that. While it's not clear how we can convert this priors, scientific priors over the functions into priors over parameters, which is why I think that it's worthwhile to think about function space view. I don't think that we have to get rid of theory. I think it's important that we make use of scientific theory which we understand. It's just that we shouldn't be shackling ourselves to models which can only express those theories and aren't flexible enough to express things that we don't understand yet. Yeah.
Thank you.
Hi. In the first few slides of your talk, you were comparing the results of your Bayesian learner with Adam optimizer. The experiment was on MNIST.
Yeah.
And so you beat Adam optimizer in a sense. But is that really the point? Do we just care about the performance? Or is it also important that we know that we have approximated the posterior, we have explored the space of good parameters?
Right.
Yeah.
Yeah. So I think it's important that we also have this posterior over parameters, and we can get kind of better, at least wider uncertainties, kind of not as certain about our predictions. And I guess I showed those experimental results because I wanted to show that we wanted to show that by thinking in a Bayesian way, even if at the end of the day you're interested in predictive performance and speed of learning, we can still do better. At least under pretty maybe toyish examples.
Thanks.
Hi, I got two questions. One is, if we don't understand what priors on parameter space actually mean, is it good to actually place them there, or is it better to just have a really wide prior so that we don't incorporate information in that? And the second one goes with the previous question about metrics for Bayesian deep learning, whether it's actually only accuracy we want to measure, or do we care about entropy out of distribution examples, or are there other things we should look into?
Okay, so the first question is whether if we don't have a good sense of prior over parameters, what should we do? I think that there is still a sense that, in the weight decay case, we want to decay the parameters towards 0, and that has to do with kind of smoothness of the function that we think it's kind of related to smoothness of functions. And I think that a sensible prior is just a very weak prior, right? In the second question, if I understand correctly, I guess I think I'm giving the same answer. It's great to have predictive distributions which are maybe more uncertain and reflects the uncertainties in the learning better. I completely agree. Yes. Yeah.
Thanks.
So thank you for your talk. Do you think a Bayesian way of thinking will help to analyze or improve GAN algorithms?
GAN algorithms?
Yes.
I think so. I think there were some recent papers on this, yeah, but I haven't read them very carefully. Yes.
Okay. Thank you.
I'm wondering how you deal with high dimensionality when you use particle filters in deep learning because of weight degeneracy. So normally in high dimensional space, particle filters suffer from those weight degeneracy, like the importance weights are different, like in a great deal. So when you're using deep models, you have high dimensional space. So how do you tackle with this?
So is the question, how do we handle the high dimensionality?
Yeah, with particle filters. When you use particle filters in high dimensional, in deep learning.
So was the question about the prior or about the computation?
About computation, because normally you will need like a high number, yeah.
Yeah, so we used this thing called SGLD, stochastic gradient Langevin dynamics. It's basically like SGD, but we just add some additional noise to it. It seems to work, I guess.
Okay.
Hi. So thank you for the talk. The question is about the posterior server. It looks like you have much information, and at this level, you could take into account the symmetries. You could have multimodal things instead of just one. I was wondering whether this is interesting?
I think it is interesting to think about the multimodalities in the posterior. It just makes the computation very difficult. So I think all the variational inference algorithms, because of this computational issue, would often just try to focus on one of the modes. That's, I think, one of the things that we don't necessarily understand very well in terms of Bayesian learning. Oftentimes, if you capture the uncertainties around the local modes at least, that's often sufficient in terms of capturing most of the uncertainty. And the actually multimodality due to the symmetries doesn't matter as much somehow. And that's something that I think lots of people puzzle over, but we don't have a good answer for.
But if I may, when you have this posterior, right, you could use the same mechanism as what you used in vivo, the fact that you might split the posterior theta into several, say, sub-distributions.
Yeah, it's possible, I think, yes. I haven't really combined the two.
Thank you.
Yes.
Okay, maybe we should just perhaps end the questions there. I mean, Yee Whye, you can perhaps ask them offline. Let's give Yee Whye another round of applause.
Thank you.